All right, some more on solutions. So this is going to get us through 3.8 and 3.9. The first one, topic 3.8, representations of solutions. So we're really looking at different problems that have the particulate model diagrams in them. And then separations of solutions and mixtures and chromatography. So learning targets using particulate models for mixtures. We represent interactions between components, represent concentrations of components, explaining the process and types of chromatography, discuss how the components of the solution interact with the mobile and stationary phases based on intermolecular attractions, and explain how distillation separates components of the solution through differences in IMFs, intermolecular attractions, with regards to the vapor pressures and the boiling points. So those are the main topics here to look at. So for instance, this was a free response question. I altered it a little bit to be a different ionic compound, but this was a free response question, I think from like 2014 or 2015. So they give you these stipulations here. The structures of water and crystal sodium bromide are represented to the left. A student prepares 1 molar solution by dissolving 10.3 grams of the sodium bromide in enough water to make 100 milliliters of solution. So the A part of this had to do with the drawing. The B part of this had to do with electrochemistry, which is totally different. But it's a very good example of how they can ask you to draw things. So in the space provided, show the interactions of the components of sodium bromide by making a drawing that represents the different particles present in the solution. Based on your drawing, the particles shown on the representations above. So they want you to kind of use their pattern up here, where you have the gray circles and the white circles. Include only one formula unit of NABR, no more than 10 molecules of water. Your drawing must include the following details. Identity of ions, so you need to make sure they have the symbol and charge in there, and arrangement and proper orientation of the particles in solution. So we know dissolution of an ionic solid, of course, is going to have those particular ions being surrounded by the water. And we only want one formula unit, so we need NABR put in there, and we need to kind of follow their diagrams there. So I'm going to make it a little bit bigger than up here, but the ones with the white circles, the ones with the darker gray circle here, which one is the sodium, which one's the bromine or the bromide? That's going to be bromide. Who knows? Which one's the sodium, which one's the bromide in our diagram up here? Yes, the BR is the gray one. Because if you look at, yes, trends, bromine is in what? The 4th row. Sodium is over here in the 3rd row. So the bromine should be bigger. It has an extra energy level, all of that. So that's what we would go with here. Let's see here. BR, no, I'll put the NA over here. Oops. Make this one a little bit bigger to be more to scale. Okay, and then it says put the charges in there. Now, when sodium and bromine separate, of course, it forms the sodium plus and the Br minus, okay, into their components. Now, looking here at the water molecules, here we have the bigger atom, of course, should be the oxygen, so that's the partial negative side, and these should be the partial positive sides on the hydrogens there. So which way should I orient the water molecules around the sodium? Oxygen in or hydrogen in? Oxygen facing the sodium, good. So now please forgive my terrible artistically challenged drawings, but that's what we would go with, the Mickey Mouse ears. Now, it says no more than 10 waters, so you could put 5 on each, or you could do, I do like 4 and 4 here, but I would make sure you draw more than one around it. And you would need to draw it kind of close because this is an attractive force between the oxygen and the sodium. So if we're drawing the oxygen in on that side, that means that the hydrogen sides should be drawn in facing the bromines, like so. And like I said, I'm going to do probably like 4 and 4 here, artistically challenged and all of that, but you would have the hydrogen sides facing inward. And that's what you would want to do here to get your points. So I think they gave like 2 points for this, and one was like the correct identity and then the correct proper orientation. So both of those points were there were 2 points for this part of the free response question. Much better drawing than what I can do there. So good luck. All right, let's look at exercise 2. And this is a concentration question. Equal volumes. So we're saying equal volumes of these vessels over here, vessel 1, vessel 2. 2 different vessels are represented above. If the solution represent 1 is NaCl, so this is NaCl, then the solution represented vessel 2 could be an aqueous solution of. Well, first thing we should probably do when we have a concentration question and looking here, of course, is read our choices. K, Br, Cu, Cl, these are kind of going to be, we have the same molarity versus twice the molarity, same molarity versus twice molarity. So that kind of gives us an idea of what we're looking for. And yes, I agree with you, we should count. Now it tells us any of the positive ions are all these dark circles. So this would be 4 positives and 4 negatives, which is a ratio of 1 to 1. All right. So I kind of need to keep that math in my head here, a ratio of 1 to 1. Over here, I've got 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 positives and 1, 2, you count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So there's 16 negatives here, which is more of a 1 to 2 ratio in terms of the particles in there. So looking at that, okay, you know, if this is like 4 particles out, you know, like the molarity, because they're 1 to 1, 4 particles out of 1 liter, so this would be like 4m. And over here, since this is a 1 to 2 of the cation to the anion, we would want to base the molarity off of the formula unit. So that would be like 8 over 1 liter. So this would be 8 molar, or at least for the positive ion and for the formula unit. So based off of that, and what I'm seeing here is that the one with the 1 to 2 ratio is going to be your CuCl2. But if I'm looking at the molarity too, the anions are, you know, quadruple what they are over here, which if it were just double, or if it was the same concentration, they would just be double since it's a 1 to 2 ratio. So I would definitely, yes, go with D, that not only do we have the formula unit that's 1 to 2, we also have twice the molarity since we have the 8 positives versus the 4 positives, which those are equivalent to their original formula units. But counting gives you a good idea. Also looking at what you have, the possibilities of your response there. Why 8 and not 16? Okay, so when we're talking about molarity, that's a good question. Okay, KBr, CuCl2, all right, so, or NaCl. If we're looking at this, you know, and we put a certain amount of grams of NaCl in there, it's going to break apart into our separate ions, right? But the molarity is based off of the formula unit. So if we're saying that this is 4 molar, that's based off of like this formula unit. If then I wanted to look at like the molarity of all the ions, not just the formula unit, it would be double because there's 2 ions per formula unit. However, over here, since this breaks apart into Cu and 2 chlorides, okay, we get one of these and 2 of those. So that's a total of 3 ions, right? So for every formula unit, you're going to get 3 ions. So if this was 4 molar, like this one over here, that means that there would be 4 positives and 8 of the negatives. Well, there's not 4 of the positives and 8 of the negatives. There's actually 8 of the positives and 16 of the negatives. So that's why it would be double in molarity. I don't know if that makes sense, but it's kind of how my brain processes it. The way that they break apart. Okay. All right, so looking here, exercise 3, this is another way they could represent it. Another multiple choice way. Of course, I added in the explain part to explain. All right, so we have silver nitrate and sodium chloride. Look for these keywords too. This is a reaction one because it's mixing. And you have dilute and excess to form silver chloride. And it's represented by the net ionic equation here. Now we're going to go into more detail about net ionic equations and review those next unit. However, these are the only things reacting. The silver and the chloride are coming together to form a bond, and they precipitate out and go to the bottom of the beaker there. So what am I looking at here really though? This tells me I have dilute. This tells me I have excess. So now out of my 2 reactants, my silver ion and my chloride ion, which one's going to run out first? Which one's my limiting? Yes, the silver is my limiting. The chloride is my excess. So when I look at my beakers, should I see any silver in any of them? Any silver ions? No, they should be gone. So this one's out. All of the silver ions should have fallen to the bottom and formed the precipitate. Since this is in excess, should I see some chloride still floating around in the water? Yes, okay. So now comparing A and C, as you can see, A doesn't have any chloride, but C does. So this would be the one that I would pick. So summing that all up again here, since the silver ion is the limiting reactant, it will run out and not be present in the solution. All of the silver ions will precipitate out. The chloride ion is in excess and will be present in the solution along with the sodium and nitrate. Now remember, the sodium and nitrate are not participating in the reaction itself. So we call those guys spectator ions. And we're going to go over spectator ions in detail next unit, but the spectator ions are the ones that still remain in solution, but they don't participate in the reaction. So they will still be floating around in the solution as well. So that's kind of another representation of how they might do a particulate model diagram. All right, let's look at chromatography and separation techniques. In general, chromatography separates the species based off of different strength of intermolecular attractions. So depending upon how attracted the components are to one another will depend on how they separate. You have a mobile phase and you have a stationary phase. The mobile phase is the one that usually creeps up the paper or the plate, and the ones that are more attracted to the mobile phase are going to have more similar IMFs than the ones that are in the stationary phase. If it doesn't move very far, it has IMFs that are more similar and attracted to the ones in the stationary phase. Stationary phase is either usually a solid or liquid supported by a solid. Okay, so paper is one of them. That would be one of those stationary phases. The thin layer one is on a plate, you'll see. And then the chromatography, the column chromatography is like in a tube, which you'll see. Looking at the paper chromatography, and we did this one in Chem 1 last year, however, not a whole lot of detailed explanation on it. You put the little ink dyes on there and then the water crept up the paper and it like split it into the rainbow colors. Great, wonderful. Well, here we're going to talk about it in a little bit more detail. The stationary phase is cellulose paper, and cellulose paper is polar. If you remember from biology, cellulose is a type of carbohydrate, and carbohydrates have lots of these hydroxyl groups on them. So that means they're capable of hydrogen bonding. The mobile phase is the solvent, and you can select a nonpolar solvent. You could select a polar solvent of a different degree, because remember the benzoic acid example where it will dissolve in ethanol just fine, but it will not dissolve in water very well. So it's a different degree of polarity here. The solvents don't have to be like as extremely polar as water. You can use other solvents like ethanol. And then you can also use non-polar solvents like heptane and octane and other things like that. Benzene's a good non-polar solvent that they use in industry. All right, so what you're going to see here is the molecules that have greater affinity for the paper than they do for the solvent, they're going to stay put. If they creep up with the solvent, they're going to have more affinity and have more similar forces to the one that's a solvent. So if the molecule is attracted to the solvent, it will travel up the paper. If the solvent has a low attraction to the solvent, it will deposit onto the cellulose paper. That means it has more similar attractive forces to the one on the paper. And the relative attraction to each compound, either the mobile phase or the stationary phase, separates out the mixture. Now, the nice thing about paper chromatography is they actually measure stuff. It's called the retention factor, or RF factor. It's basically the distance traveled by the component divided by the solvent front is what it's called, solvent front, okay? So it is like a decimal proportion of how far it travels. So here, though, I gave you an example of when it doesn't completely separate and you have kind of like the blob traveling up. Then you just want to average it to the middle. This is what they're doing, is they take the A and the B and they average it. So you get the correct distance here in the middle. And I suppose you could probably just measure it off of the middle if you really wanted to, but and then they divide it by the solvent front. In this case, the solvent front was labeled D here underneath there. And measuring the retention factor is a helpful key, especially when you're trying to identify unknowns. Exercise 4 is actually a free response question from the 2017 AP exam. And this was the first time we've seen chromatography pop up as a free response question in a very, very, very long time. But I can imagine it's going to pop up again soon, so definitely want to touch on it and make sure you can process this information carefully. Here they do the setup for you on this side. You're looking at the diagrams. You have all three dyes and an unknown, two separate chromatography chambers, but you should key into this part. The solvent is nonpolar. So that's what they're telling you initially. All right, and then over here is the developed chromatograms. This happens to be the results, okay? And what you're going to interpret about them. Now, reading through the information, student investigates various dyes using paper chromatography. The student has samples of 3 dyes and an unknown. The student prepares them above, as you can see, indicated by the position on the chromatography paper. But this is the important part that you need to pull out of here. The paper itself is polar. The solvent is non-polar. All right? These two things, important here. The developed chromatograms are shown over here to the right. Which dye, A, B, or C, is the least polar, or the most non-polar, I suppose, is another way you could say that. Justify your answer in terms of interactions between dyes and solvent or between dyes and paper. So you have 2 choices of how to explain it. So which one is going to be the least polar? Is it going to stick to the paper, or is it going to travel up with the solvent? Yes, it's going to be dye C. It's going to be the one that travels farther up with the solvent if it's least polar, because the solvent is nonpolar. All right, so that's correct. Now you could say, if you're referring it to the interactions between the dye and the solvent, you could say the least polar one, since the solvent is nonpolar, the least polar is going to travel the farthest with it because it's the most attracted to the solvent, having similar forces of attraction. Between the dyes and the paper, what you would say, the least polar one is also C, because it traveled farther, because it's less attracted to the polar paper. Less attracted to the polar paper than it is to the solvent, okay? So here are the two ways that the scoring guidelines talked about it. Dye C is the least polar because it traveled the farthest, being strongly attracted to the nonpolar solvent. Or you would have gotten the point if you put dye C as the least polar because it traveled the farthest, being least attracted to the polar paper, the chromatogram paper. Either way, you would have gotten the point there. Now, there's one other point to this particular. No, you would just have to write it one way. That's all. So you pick which way you're more comfortable writing it. Which dye is present in the unknown sample, and justify your answer? Well, now we need to really look and investigate, stuff going on here in our developed chromatograms. Here is our unknown. Here are our three dyes. Let's take a look here and try to compare. One thing should stick out to you immediately, though, that is not going to line up right. What is different about the two different chromatograms? The different heights of the solvents. So it's a little bit more tricky to judge exactly. So this is when the retention factor idea comes into play, and it's helpful. You have your, traveling up here B, you have yours to the here A, so A over B. If you look between here, guess what? That's about halfway. So that's about 0.5. If I look at this one, traveling up, and I want it to be about halfway, well, which one's about halfway? Dye A, which makes sense, right? Yes, dye A is about halfway. So we're going to justify our answer. You could have phrased it in one of two ways. First, make your declaration that it's dye A is the one that's in the unknown. So you have to first make your claim which dye. So dye A is the one in the unknown. Now, it's the one that traveled approximately halfway between the origin and the solvent front, as dye A did. Or you could say both dye A and the unknown have retention factors that are approximately 0.5. Either or, you can use either or in order to explain, but make sure that you're justifying and comparing together. Actually, yes, the College Board releases all of the old free responses, and you can find them on AP Central. If you search for them, you will be able to see all prior free responses that have been released. You can also Google, and you'll find a lot that way. You can say AP exam 2008 chemistry free response, and it should show you what they look like. Well, it depends on if it was before 2012. They changed the test over in 2012. So before 2012, I think there's more free response than there is after. And before 2012, they had people do reaction writing. Reaction writing is no longer required. So that part and component of the test is no longer like something you would need to do. I still would encourage you to look at prior free response questions to 2012, just to kind of ignore the reaction writing portion of it. Those questions are still pretty good. And there's a few slight changes to the curriculum, but for the most part, they're still very good to study and look over the scoring guidelines to check out how they're phrasing their answers. I can't even tell you how many hours I have spent looking at old exams and looking at their scoring guidelines to try to figure out how I should say things. So that would be an excellent study tool. And you can Google like chromatography free response questions, AP exam, AP chemistry exams, and it should narrow it down for you to try to find the years that had those particular questions on there. But like I said, a lot of the questions though are merged. So it might start off as a chromatography question and then evolve into other questions from other units. So keep that in mind. On our AP exam for May, you have 3 long questions that have like 10 points each, and then you're going to have 4 short questions that are like 4 points each. Let's look at the thin layer chromatography. The stationary phase is a plate that contains a silica gel. And if you look at your diagram over here, you're going to easily be able to tell that it's polar because of all of these hydroxyl OH groups that are going to be able to engage in hydrogen bonding. Now the mobile phase could be a liquid or a gas depending upon what kind of equipment you have, but it's basically going to do the same thing as the paper one. If it's more attracted to the solvent, it's going to creep up with the solvent. If it's more attracted to the plate, and the silica gel, it's going to not move very far. So this one's very similar to paper one, except for now you've got the silica gel that's been, backed by a plate that has aluminum foil on it. But let's look at an example of the thin layer chromatography. I found this one online. I feel like it's pretty good. So for looking at exercise 5, explain why P travels farther along the plate than SM when acetone is used as the solvent. Well, here's acetone, okay? I gave you the structure. I don't expect you to know acetone off the top of your head. And a lot of times in the free response questions, they'll give you the diagrams and so forth to help you justify your answer. For those that don't know, acetone is the main component in fingernail polish remover. So it's a polar substance in there. Now, I know it's polar because the dipole moment goes towards the oxygen, so this is partially negative. So what type of interactions or intermolecular forces is acetone going to engage in? Or the most predominant intermolecular force, I should say, the most predominant is going to be dipole-dipole. Yes, so these are dip-dips. All right, now, so that's my solvent. I know my silica gel has hydrogen bonding, okay, because of those OH groups, hydrogen bonding. So now we're looking at slightly different things. Both substances are polar, but one is more polar than the other. So the silica gel in this case would be more polar than the acetone. Now let's look at our 2 materials. We have our starting material and our product over here. They have 2 components that are pretty much the same. We have a benzene ring and a nitrous group. Now this nitrous group is definitely polar, and that's gonna, these will be dipole-dipole interactions down here for this side of the molecule. The benzene rings, of course, are more nonpolar. But if you're looking at the top of these, this is OH. This is, I know it's hard to see, but here I'll just draw it. It's the O, and then the O is bonded to a CH3 group like so, okay? And this is actually not a double bonded O, it's a, I did too many dots there, but it's actually more of an ether type O, like so. And this is the benzene ring here. Now, looking at this thing right here, what kind of forces is it going to be on this side of the molecule? My H doesn't look very good. There we go. What kind of forces will this side have? Yes, this would be dipole-dipole as well. Okay, because we have the dipole moments going towards the oxygen. So this is definitely going to have like a slight negative right here. Over here though, OH, what kind of forces is going to be in that particular starting material on that side of the molecule? Hydrogen bonds, okay. So the main difference between our things here is that this one does hydrogen bonds on the top, this one does dipole-dipole on the top. The rest of it's all equivalent. So if we're looking here at our dots, they're starting points and ending points. The one that traveled farther, of course, is P. Why is that? Because our solvent has dipole-dipole interactions that are more matching of the dipole-dipole interactions of product, whereas the starting material has that hydrogen bonding, so it's more attracted to the hydroxyl groups on the silica gel. So starting material has hydroxyl groups capable of hydrogen bonding, which attract more strongly to the silica gel. The product is polar with only dipole-dipole interactions that would be more strongly attracted to the acetone in this particular case. Lots of fun for that one. That one's a little bit more tricky, but I could see them asking something like that, giving you the structures and having you figure out the intermolecular forces. Column chromatography. Basically, you have a column, it looks sort of like a burette, and they can be larger in size, so you can actually do more material separation with this type of experiment. They do this more in industry to separate components of mixtures. I think the mobile phase, the solvent, is known as the eluent right here. So basically what you do is you dump solvent in there and it washes down through the burette. But in the burette, you have this alumina, which happens to be the stationary phase. This is the stationary phase. And it's basically made of that silica gel stuff, that polar stuff. So you can wash it down with non-polar solvent, or you can wash it down with, slightly different polarity on the polar solvents. But what you're going to see here, as your sample is separating, the washing comes in, starts washing it down. The one that is more strongly attracted to the silica gel, the stationary phase, is not going to go down as fast as the one that's more attracted to the solvent. So when it says weaker attractions here, it's referring to the stationary phase. It would be, you could also say it's more strongly attracted to the eluent or the solvent that's being washed down the column. And then basically at the end, you could just put like a beaker here, and then you open your, toggle switch here, and then it ends up going through, and you can separate out your components of your mixture easily and fill up one beaker with it, and then fill up the other one over here with the other substance in the mixture. I haven't really seen any formal free response questions on column chromatography. It's more about paper and thin layer, but I have seen some multiple choice questions. And yes, it is used to separate larger amounts of solutions and mixtures. So this type, especially if you have a big enough tube or burette, and some of this glassware can be made very largely, and I'm sure the ones in industry do this, but it will an easier way to separate large amounts. All right, talking about distillation. We briefly cover this as well in Chem 1. Distillation is, of course, two liquids are in the flask. Different boiling points is what we're looking at here to separate them out. Of course, the one with the lower boiling point should evaporate faster and end up in the condensing tube. And then, of course, you have water in, water out that cools this off, which makes the gas condense back into a liquid and come out the other end. Now, remember, vapor pressure plays a role because every liquid has a certain amount of vapor pressure on top of it. The one with a lower vapor pressure obviously has a higher boiling point and stronger IMFs. Remember that a liquid does not boil until the vapor pressure equals the atmospheric pressure. So that's the definition, of course, of getting to that boiling point, that temperature at which the vapor pressure is equivalent to the atmospheric pressure. So problem is, though, if you're doing regular distillation here, a lot of times there's going to be vapor pressure in there from both liquids, regardless of whether or not, they have differing boiling points. So in order to completely purify the substance, especially if they have closer boiling points, is to use fractional distillation. Now, fractional distillations adds a larger column here that allows for some vaporizing and condensing, and usually the one with the lower vapor pressure doesn't, or they hope to not make it all the way up the tube and come into the condenser. Sometimes though, when performing distillation, especially when you need really pure substances, like for fuels and for distilling alcohol, they'll have to be repeated a few times in order to make sure your substance is very pure. Like for instance, in taking a sample of alcohol, you would have to make sure that, because when you have a sample of alcohol, though you might have the majority of ethanol, there might be other alcohols in there, and of course you wouldn't want methanol in there because it's quite toxic and would cause, you know, serious health implications if that was like manufactured and wasn't properly distilled out of like those that manufacture beer, wine, and other products like that. So fractional distillation really is more for purifying. It has the extra added component. It's more time consuming, takes more energy, obviously. So here's an example for the crude, for refining, getting the different fuel types. Simple distillation would just be basically more for like purifying seawater. It's not as precise. Okay. I did want to show you a short little video of graphing them on the curves there, and how the fractional curve looks different than the simple distillation curve. So let's take a look at that real quick. Okay, so after looking at that video, taking a look, what you should notice, obviously, the graphs are distinctly different. One shows you two distinct boiling points, and the other one's more of a gradual one. And also, like he was saying, that you could collect the one and then in between, you know, the other phase, switch out and have another beaker to collect the other one later. So being as it may, the fractional one is a better method of really trying to truly get pure substances, especially when the boiling points are relatively close to one another. About half, maybe half of the methyl acetate out, because at that point in the mixture that's still left inside the flask in the beaker, it's more propyl acetate than it is methyl acetate. And so it needs to get closer to the propyl acetate boiling point to keep boiling at that point, because your mixture has really like lessened. It's not as much of a mixture. So that would be why I would say you'd have to increase that temperature to get the rest of the methyl acetate out. Remember, I don't know if you got to talk about colligative properties of mixtures, but a pure substance on its own has its own boiling point. But if you add solute to it, the mixture is always going to have a higher boiling point than the original pure substance, depending upon the number of particles in that mixture. And in order to, occur for that, and that's why originally you can't just like heat it to 56.9 and then the methyl acetate comes out. The boiling point's actually a little bit higher because it is a mixture of both of them. And you have to, increase it to, he said, initially to get the methyl acetate to mainly start to come out would be about halfway between the boiling points. So you're not getting close enough to boil out the propyl acetate. And distinctly get the one layer from the other layer, basically, in terms of that graph. All I really wanted to show you, though, is that the fractional distillation is used mainly more for boiling points that are close together, and it's mainly used for when you have to separate out and purify things. So even, fractional distillation for oil that you're going to refine into fuels or alcohols, there's multiple steps to it, and it isn't just like one quick distillation process. Now, last but not least here, evaporation, just a quick review. Even though it's not formally in the topics, I have seen some questions referring to evaporation. hopefully, you know, you have the common sense of this one that yes, if you have salt water and you boil out the water, the salt is going to be left behind. Those solid crystals, the white crystals of sodium chloride would be left behind, and you can use evaporation to separate solid solutes from their liquids in order to separate them into their two separate components. Now, evaporation isn't great if you're trying to collect the solvent, because obviously that one just completely evaporates out.